Imagine waking up one day to realize that everything you have ever experienced, every sensation, every memory, is not the fundamental reality, but rather a complex, computed simulation running in a system far beyond our universe. This sounds like science fiction, yet leading physicists, computer scientists, and philosophers discuss it seriously as a plausible scientific hypothesis, exploring whether our universe could be computational at its core. The central question is both simple and unsettling. Is the universe truly fundamental, or is it an advanced computational construct running according to hidden rules that determine every particle, star, and moment of consciousness? If reality is a simulation, then space, time, matter, and even consciousness are outputs of an underlying information process, carefully orchestrated and executed at a level we cannot perceive directly. This is not about extraterrestrial entertainment. It is about the possibility that information, rather than matter, forms the foundation of existence, shaping the universe according to rules beyond our current understanding. To see why this idea has credibility, we need to rewind human history and examine how our understanding of reality has repeatedly been overturned by revolutionary discoveries. For millennia, humans assumed the universe was solid, continuous, and objective, a stable backdrop where events unfolded predictably and independent of observation. That certainty began to erode as physics revealed that reality behaves very differently at extreme scales, from the vast cosmos to the subatomic world. At the smallest scales, particles exist as probabilities, not fixed objects, and only take definite positions when observed, revealing a universe that is less solid than previously imagined. This behavior implies that reality itself may not exist fully until information is extracted from it, a concept that challenges our intuition about the world. Even more astonishing, the universe is governed by strict mathematical rules, behaving as if it follows an algorithm, a framework of logic running reality like a program. Everywhere scientists look, they find limits, the speed of light, the Planck length, and discrete energy levels, hinting that spacetime itself may have a resolution, like pixels in a computer display. Modern physics treats information as a real, conserved quantity. It is not abstract. It behaves physically and can influence the universe at the most fundamental level. Black holes, the most extreme objects in the cosmos, encode information on their surfaces rather than inside, as if reality itself has a boundary layer of data. This leads to the holographic principle. Three-dimensional space may emerge from two-dimensional information, suggesting that our universe is more like a projection than a solid object. Around the same time, advances in computing demonstrated that complex, seemingly lifelike worlds can emerge from very simple rules executed repeatedly over time. Video games showed that entire ecosystems, physics, and even emergent behaviors can exist purely as calculations constrained only by processing power. As computing power increases, simulated environments grow more detailed, convincing, and autonomous, eventually capable of containing conscious-like entities. This possibility leads to a profound question. If minds can exist in a simulation, are the majority of observers in the universe actually simulated? Philosopher Nick Bostrom formalized this as the simulation argument, reasoning that at least one of three possibilities must be true about advanced civilizations. Either civilizations go extinct before achieving simulation technology, choose not to run simulations, or we are almost certainly living inside one. If even one civilization survives and runs many simulations, the number of simulated minds would vastly outnumber real ones, making it statistically likely we are simulated. Probability overwhelms intuition. A randomly selected observer is far more likely to be simulated than real, forcing us to confront uncomfortable possibilities. Physics hints at computational limits. The speed of light, the Planck length, and quantized energy levels suggest the universe may operate like a digital system. Even randomness in quantum mechanics may be algorithmic, suggesting that what we perceive as chance may emerge from a deeper computational process. Some scientists speculate the universe functions like an error-correcting code, maintaining stability while evolving, ensuring that reality doesn't glitch. Patterns in physics appear optimized, balancing complexity and efficiency, much like how programmers optimize simulations for performance and realism. None of this proves we live in a simulation, yet the coincidences and mathematical elegance challenge our assumptions about fundamental reality. The hypothesis forces us to rethink existence, consciousness, free will, and meaning may all emerge from computational processes we barely understand. Even if simulated, the universe still feels real from the inside. Experiences, emotions, and discovery retain their significance, challenging us to explore and understand it fully. Some physicists speculate that the randomness of quantum mechanics is not truly random, but emerges from an underlying computational algorithm that governs the universe at a deeper level. The universe may function like an error-correcting code, maintaining stability, repairing anomalies, and ensuring continuity in ways that hint at a deeper informational structure. Patterns in physics appear optimized for efficiency. From planetary orbits to galactic structures, everything seems arranged with purpose, much like a simulation optimizing resources. These patterns are reminiscent of how programmers design simulations, rules, constraints, and efficiencies embedded within a coherent system producing complex behavior. While this does not prove we live in a simulation, it challenges the assumption that our universe is purely natural or accidental. The idea forces us to reconsider what real truly means and whether our sensory experiences reflect a fundamental substrate or a higher-level computation. If simulated, the laws of physics themselves may be nothing more than programming rules, setting limits, defining interactions, and shaping the behavior of matter and energy. Consciousness might then be a form of software, running on biological hardware, experiencing reality from within while being generated by a deeper computational layer. Yet even if our minds are simulated, the experiences we have, pain, joy, memory, discovery, remain real to us and meaningful in shaping our lives. Emotions, relationships, and achievements retain significance, whether or not the universe beneath them is simulated or fundamental. The simulation hypothesis does not devalue life, it reframes it, suggesting that even if computed, experiences are meaningful and reality is deeply rich. It reminds us that reality may be far deeper than our senses perceive, layered with complexity we have only begun to understand. If simulated, the universe could have purpose, rules, or constraints set by an intelligence far beyond our comprehension. Alternatively, it could exist simply as a byproduct of advanced computational processes, running silently without intention or awareness. Detecting whether we are simulated may be impossible. An advanced system could hide its computational tracks perfectly. The absence of evidence does not rule out simulation. The universe may appear seamless precisely because it is engineered to be consistent. Science can only explore the observable universe. It cannot probe what lies beyond the system it inhabits. Yet the very act of asking whether reality is simulated reshapes how we think about consciousness, physics, and existence itself. It pushes humanity to question assumptions, explore limits, and probe the deepest foundations of existence. Even if we never detect a simulation directly, contemplating it inspires new science, philosophy, and technology. Each era in history believed it understood reality fully, only to have its models overturned by new discoveries. From Ptolemaic to Newtonian to quantum physics, human understanding of reality has been repeatedly rewritten, challenging our sense of certainty. The simulation hypothesis may be this generation's revolutionary challenge to certainty, urging us to rethink the nature of reality. Whether true or not, it forces us to ask better questions about consciousness, free will, and the ultimate structure of the cosmos. Even if simulated, reality still obeys discoverable rules, allowing science to explore, predict, and manipulate it meaningfully. Meaning, morality, and purpose do not vanish simply because the universe is computational. Our experience remains rich and consequential. If anything, existence becomes more mysterious and awe-inspiring, highlighting the extraordinary depth behind what we take for granted. We may never see what lies beyond the universe or the system containing it, but the questions themselves push the boundaries of human thought. Each attempt to understand reality, from ancient stargazing to modern quantum physics, reveals the fragility and wonder of our knowledge. Asking whether reality is a simulation may be the most profoundly human question of all, blending curiosity, awe, and the quest for truth. To explore the simulation hypothesis further, scientists examine whether subtle glitches or constraints exist in physics that hint at underlying computational rules. One idea is that the universe has a maximum resolution, discrete spacetime units, energy quanta, and limits like the speed of light resemble computational constraints. These limits may be analogous to pixels on a screen. Reality appears continuous, but at its smallest scale, it may be digital. Even randomness in quantum mechanics may be algorithmically generated, suggesting events we perceive as random are constrained by hidden rules. Black holes offer further hints. They store information on their surfaces, implying that 3D reality emerges from 2D data layers. This holographic principle suggests our universe could be a projection, with information encoded on distant cosmic boundaries. Simulations also demonstrate that simple rules can create extremely complex, lifelike behavior, as seen in cellular automata and advanced AI. If advanced civilizations can run trillions of simulations, most conscious observers could exist inside a simulation rather than base reality. Statistically, the likelihood of being simulated becomes significant, forcing us to reconsider our assumptions about existence and consciousness. Even if we are simulated, our perception of reality is internally consistent, obeying discoverable rules, allowing science and exploration to function. This opens a profound philosophical question. Does simulation make life less real, or is reality defined by experience and interaction? Consciousness itself might emerge as a computational process, generating subjective experience regardless of whether the underlying universe is fundamental or simulated. Even if simulated, experiences of beauty, love, and curiosity remain real to the observer, reinforcing the meaningfulness of life. The simulation hypothesis challenges our understanding of free will. Choices may be influenced by computational rules, yet remain subjectively real. Some scientists argue that detecting simulation constraints may be impossible, as a highly advanced system would perfectly mask its tracks. Even the most extreme events, like black hole mergers or quantum fluctuations, could be fully consistent within computational rules. Our physical laws may themselves be emergent, rules coded into the system to produce a consistent, observable universe. Meaning, morality, and purpose remain intact, as experience and consciousness persist, whether fundamental or computational. Considering the simulation hypothesis encourages exploration and discovery, inspiring new ways of thinking in science and philosophy. Each era in history believed it understood reality fully, only to be challenged by new discoveries that reshaped knowledge and perception. From classical mechanics to quantum physics, human models of reality have evolved, revealing the fragility and provisional nature of certainty. The simulation hypothesis is our generation's equivalent, a radical challenge to intuition and assumption about the universe. Even if unprovable, the hypothesis motivates new questions about consciousness, computation, and the structure of existence. The question of simulation reframes discovery. Our goal is not only to understand matter, but the informational rules that govern it. Life and reality may be richer than imagined, filled with rules, patterns, and emergent phenomena beyond what we can perceive. Even if simulated, our experiences remain consistent, meaningful, and awe-inspiring, preserving the human sense of discovery. Simulation, if it exists, does not diminish the reality we feel, it emphasizes the depth and mystery of existence. Contemplating this possibility strengthens science, philosophy, and curiosity, pushing us to ask deeper questions about reality itself. It encourages humility. We may never see beyond the system, but the questions themselves expand the boundaries of knowledge. Asking whether reality is a simulation may be the most human question of all, blending curiosity, awe, and the relentless quest for understanding. As we explore this question, the boundary between science and philosophy blurs. Understanding the simulation hypothesis requires thinking about both physics and consciousness simultaneously. Even if our universe is a simulation, it remains internally consistent, allowing stars to form, life to evolve, and consciousness to emerge according to predictable rules. These rules might be optimized for stability, efficiency, and complexity, much like a sophisticated program designed to maintain a vast, consistent world. Observing the universe carefully, we may detect subtle hints, constraints, patterns, or anomalies that reveal the computational nature of reality. Yet the system could be perfectly designed to hide its tracks, making it impossible to distinguish fundamental reality from simulation from within. Regardless of proof, the simulation hypothesis inspires profound curiosity, pushing humanity to explore physics, computation, and the nature of consciousness. It reminds us of the fragility of knowledge. History shows that our understanding of reality can be repeatedly overturned by new discoveries. The simulation hypothesis is our generation's intellectual frontier, challenging assumptions, encouraging exploration, and reframing what it means to exist. Even if unprovable, asking the question drives science and philosophy forward, inspiring curiosity and new perspectives on reality. Consciousness may be computational, emergent, or real. Regardless, subjective experience defines meaning and allows exploration, discovery, and emotion. Our perception of the universe, whether simulated or fundamental, is internally consistent, allowing science, curiosity, and wonder to flourish. Simulated or not, experiences of love, curiosity, joy, and discovery remain fully real to the observer, shaping life's meaning and purpose. Considering simulation expands imagination, pushing us to explore deeper questions about reality, computation, and consciousness. Even if the system conceals its origins, probing physical laws, cosmic structures, and consciousness brings insight into the mechanisms that govern reality. Life retains value, significance, and awe. Experiences are meaningful whether fundamental or generated by a higher computational layer. Even simulated existence is remarkable. Stars, galaxies, and life emerge consistently, following rules that allow complexity to flourish. Understanding that reality could be computational does not diminish it. Instead, it emphasizes the beauty, intricacy, and mystery of existence. We may never detect the system or see beyond it, yet the very questions challenge and expand human knowledge and imagination. Each exploration, observation, and thought pushes the boundaries of understanding, whether reality is fundamental or computational. Considering simulation allows us to embrace humility, awe, and curiosity, acknowledging the limits of perception while striving to understand. The idea also encourages technological and philosophical innovation, inspiring AI research, computation, and inquiry into the mind itself. Even without proof, contemplating simulation strengthens science, philosophy, and human imagination, encouraging exploration of the deepest questions. The hypothesis invites reflection. What defines reality? Is it experience, observation, or an underlying computational framework beyond perception? Reality, whether simulated or not, continues to obey discoverable rules, allowing science, curiosity, and human experience to flourish meaningfully. Asking these questions transforms the way we perceive existence, emphasizing the interplay between consciousness, physics, and information. Even if life exists inside a computational framework, our emotions, achievements, and experiences are real to us, retaining significance and wonder. Simulation, if present, only enhances mystery. The universe becomes richer, deeper, and more awe-inspiring than we ever imagined. The ultimate truth may remain hidden, but the act of questioning expands knowledge, imagination, and our ability to explore reality. Each discovery, from ancient astronomy to quantum physics, prepares us to ask bigger questions, including the possibility of a computational universe. Asking, are we living in a simulation, may be the most human question of all, blending curiosity, awe, and the relentless pursuit of truth.